All right, ladies and gentlemen. So, last topic we're going to discuss for chapter 25 for now is this idea of mass extinctions. So, when we look at mass extinctions and we look at the fossil record itself, we see these huge periods of diversity of life building and building and building, and then they get slammed by these periods of mass extinctions. So, if we look at this graph here, right, here's your extinction, we're building up diversity again, and we get slammed by a mass extinction event. Same thing again, mass extinction event. But all of this is correlated to an overall upticking trend of increased diversity over time. So these mass extinctions are a result of huge disruptive global changes, right? Huge environmental changes. And the species that exist at the time aren't capable of dealing with that rapid change. So as a result, you can't adapt, you go extinct. We see the fossil record showing that there are 5 mass extinction events in Earth's history. That being said, there are multitudes of small extinction events that are going to occur throughout all of Earth's history. But when we talk about those big boundaries between geologic time, these major mass extinction events are the ones that really color where we draw those lines. And when we talk about mass extinction events, we're talking about killing off more than 50% of Earth's species that are alive at the time get wiped out. And they get wiped out in a relatively short period of time, geologically speaking. So let's talk about a few of them. So Permian mass extinction, this one defines the boundary between the Paleozoic and Mesozoic eras about 251 million years ago. And this particular mass extinction claimed 96% of marine species, 8 out of the 27 orders of insects, and occurred in less than 5 million years. Why do we think it happened? Well, there appears to be information in geologic record to suggest intense volcanic eruptions occurring in what is now Siberia. All of that chemicals and ash and rock and dust gets thrown up into the atmosphere, really ends up blanketing the Earth in these huge CO2 levels, causing rapid global warming, and it ended up reducing the temperature gradient that had existed from the poles to the equator. So basically, it warms up the upper ends of the hemispheres, and there really is less of a distinction in temperature between the equator and the poles. Also ends up producing a really anoxic environment in the oceans, reducing the ability for ocean waters to mix, slowing down currents, if not stopping them entirely, which is also where that temperature gradient kind of disappears from, because moving those waters around would have been what keeps climate going as well. Cretaceous mass extinction is probably the one that most students are familiar with, and this one followed the Jurassic period 65 million years ago, so this is our boundary between the Mesozoic and Cenozoic eras. Doomed more than half of all the marine species existing at the time, exterminated tons of terrestrial plants and animal families. What most students know from this particular mass extinction is because this also included the extinction of the dinosaurs. So the suggestion is that this particular mass extinction event was a result of a large asteroid or comet colliding with Earth. And as a result of that collision, hitting Earth, spewing all sorts of rock and dust and debris up into the atmosphere, and really sort of clouding out the sun for enough periods of time. Suggestion is that the Chicxulub crater in the Caribbean Sea near the Yucatan Peninsula was created about 65 million years ago based on its discovery and its dating, we also see a thin layer of iridium enriched clay, which typically is a result of some sort of impact by a extraterrestrial object. And this crater is huge. It's in and of itself 180 kilometers in diameter, back calculating, suggesting the object that hit us was about 10 kilometers in diameter. So it was a pretty big impact. So take that plus the timing and what would have happened as a result of the fallout of that collision. It seems to be a likely hypothesis as to what could have killed off all of these organisms in this mass extinction. And then there's a question of, are we currently sitting in a sixth mass extinction? And I think more and more as time passes, data becomes available, scientists are saying this is probably the case. We're currently looking at an extinction rate that is somewhere around 100 to 1,000 times the typical background rate that we expect to see. As just typical extinction events, typical organisms disappear. So we're saying that this increased trend in warming of global temperatures across the board, this climate change that we're seeing as a result of human activity, seems to suggest that we are very much likely sitting in a sixth mass extinction. Is there some potential for us to reverse it? Perhaps. Should we probably be trying to reverse it as much as possible? Probably, because the global trends that we're seeing in temperatures are clearly associated with things that we're doing. We take a look over Earth's history and we know that there's trends of warming and cooling of Earth, but what we're seeing is the extreme end of that trend, above and beyond what we have seen in Earth's history previously. What's the only difference? Us and the Industrial Revolution and the things that we have been doing. So moving towards sustainable energy, reducing our dependence on carbon dioxide emissions and things like that, is probably a good idea. So if we look through geologic history, right? Remember I showed you that graph at the beginning of this video that we'd see these peaks in mass extinctions, but overarchingly we see a trend in increased biodiversity, even though we're killing off major amounts of life every time. And the reason being, what are the consequences of these mass extinctions and how are we seeing that increase in diversity? Think about it. If we're building up this biomass, right? These organisms are doing their jobs, increasing their populations. We end up running out of space. We end up running out of jobs for organisms to do. And so when we come in and have this major die-off, remember that organisms have a big distinction between their potential niches and their realized ones. Go back to the ecology piece, right? There's a lot of organisms who could do a multitude of jobs in their ecosystem, but are limited to just one because it's the one that they are capable of filling best. We get a mass extinction event to happen, and now all of a sudden we open up a bunch of niches. And so as a result, those organisms that survive are now capable of spreading out into those niches that have been opened by those extinct organisms. And so there's potential for new evolution and new change to occur. So when we look at this, it can take anywhere from 5 to 100 million years before we rebuild the biodiversity we started with, or increase the biodiversity that we had prior to the mass extinction event. But it paves the way for adaptive radiation. And really, adaptive radiation is just that. We start off with that ancestral species, and they adapt and radiate out to fill those voids in the ecosystems left behind by those extinct organisms. So they adapt into those different niches. It can follow those mass extinctions, but that's not the only way adaptive radiation can occur. If we get some evolution of some novel characteristics, that can also cause adaptive radiation to happen. Um, or just colonization of new regions is another common one. When we start getting to talk about Darwin and Galapagos and the finches, that was a big driving force behind the finch adaptive radiation, the finch evolution. Figure here also shows the Hawaiian archipelago, which also takes this ancestor of a tarweed, gets spread out to the different regions of Hawaii and become all of these diverse organisms, these diverse plants as well.